Thank you very much, everybody, for coming. Today's workshop is Fusion 360. It's the third one of the year. It's hosted by Gabby, who's a Fusion 360 expert from Autodesk. Here we have our designathon in less than a month. So please stay tuned for that. You can find more information on our website. And this workshop, along with our others, can be found on our website and on our YouTube channel at utdl.tech. Gabby, thank you very much for coming today, and I'll hand it over to you.
Thanks, Kyle. So today the topic is advanced fusion, which I think the subtext for was simulation and generative design. So that's what I'm going to talk about today. I'm mostly going to talk about generative design, but I'm going to start off with fusion or with simulation for a bit. And I guess we didn't really talk about this, but I think the designathon is going to use some simulation principles, and hopefully folks will use some generative design as well. So let me share my screen here. Oh, can you enable screen share?
Oh, yes, sorry.
No problem.
There we go. That should work.
Okay, 1 second. Yeah, there we go.
Perfect. Thank you.
Okay, so let's talk about simulation. So I guess who's been to a fusion workshop before? That'll kind of tell me how much I need to skip. So if you've been to a fusion workshop before, can you like put a thumbs up or a check mark or something? Okay, so a couple people have not. All right, great, thanks. So Fusion is a platform for end-to-end product development. I just realized my video is not on. There we go. It's a platform for end-to-end product development. It has pieces of basically every process you'll need to develop a product. So it has a CAD platform, it has an optimization platform, it has a CAE or computer-aided engineering or simulation platform, and it also has a manufacturing platform. So today we're going to be talking about the CAE simulation and also the optimization piece. So starting with simulation. So I guess where to begin. So simulation is a tool, right? Built into Fusion 360. It's built into some other CAD programs as well. It's also there's also a lot of standalone software that just does simulation, thinking of like ANSYS, COMSOL, Autodesk CFD. Yeah, those come to mind as well. But essentially what the point of simulation, or FEA as it's also called, which is a type of simulation, which is finite element analysis, it's a method of simulation, is to test your designs for the real world before you actually commit to making them. So if you design a beam, for instance, you want to make sure that your beam can withstand heavy loads before you build it. So you would take that design into the simulation space and put loads on it, and the software would basically compute how the model is going to respond to those loads, and then give you the results and tell you, you know, it's high stress in these areas, it's high strain in these areas, it's the factor of safety is too low, it's going to fail, it's not going to fail, and then you as a designer get to make judgments about what to do about that. So that's simulation in a nutshell. That's why you do simulation. That's the purpose of the tool. So in Fusion, there are many types of simulation you can do. This beam, loading on a beam is maybe the simplest type, but we'll go through that in a second. So one thing that's really nice in Fusion is for folks starting out in the simulation space, if you don't know what type of simulation you're going to make, you can basically open the simulation workspace and find descriptions of every type of simulation we have and what it's used for. Oh, whoops, Fusion is opening in the background. 1 second. Okay, here we go. Okay. So Fusion is unique in the sense that these simulations these simulation types that it has are powered by Nastran in the cloud. So Autodesk Nastran is our solver. It is a FEA solver for multiple applications, Fusion being one of them. It also is the backend for Inventor, Inventor FEA as well. But the unique thing about Fusion is that you can solve these studies on the cloud. So typically, on, first gen CAD platforms or first gen products like SolidWorks, Inventor, AutoCAD, if AutoCAD even has simulation, which I'm not sure of. When you're doing these memory intensive tasks, like running a simulation, you're forced to do it locally. And what that means is that you're going to tie your computer down for potentially hours running really computationally intensive studies. And the nice thing about Fusion is that you can actually run those on the cloud so that you don't, bog down your computer with having to run them, and that would disable you from doing anything else basically for that entire time. So it runs them quicker, it frees up your local computer, and it's free for students. Okay, so now on to simulation types. So there are, I believe, 9 types of simulations that we currently have in Fusion. So I'll go over each of them, but I would guess for the Design-a-thon, you're probably not going to be using all of them. You might be using a couple. So quickly, so linear static stress is a simulation type for basically linear materials that are experiencing static stresses. So a static stress is a type of load that's not moving, that's not dynamic. So like if I'm pushing on a beam or I'm sitting on a beam and I'm just staying there sitting, right? That's a static load. That load is just there. And linear refers to the type of the material, or refers to the behavior of the material. So for example, any metal would be a linear material. A nonlinear material would be like an elastic or something like that, where the stress strain curve and the material response is nonlinear, right? Doesn't follow a typical graph. So that's linear static stress and nonlinear static stress. That linear versus nonlinear refers to the type of material, because depending on if the material behaves linearly or nonlinearly, the solver is going to be a little bit different. Okay, so modal frequency is a type of simulation where you're trying to figure out what the natural frequency of the part you designed is. So this is pretty important for designs that are in the natural world, like bridges or buildings, right? Everything we make has a natural frequency, otherwise known as a resonant frequency. And what we design, we want to make sure that doesn't match. The things we design don't have a natural frequency that matches the natural frequencies that they would see in the real world. Because when frequencies basically match, they get amplified. So you can think of like a sine curve, 2 sine curves together doubles the amplitude of the sine curve. So an example of like really a disaster with a a modal frequency failure would be like a bridge collapse. You know, you've seen these videos probably where like the wind hits the bridge at just the right frequency and then the bridge starts swaying and then collapses. That's a case where the natural frequency of the wind matched the natural frequency of the bridge, and thus the amplitude, you know, multiplied, and then the bridge collapsed. So we do modal frequency analyses to find out the natural frequencies of the parts we're designing, so we can make sure those don't match the natural frequencies of the real world that they will encounter. Okay, thermal is what it sounds like, right? It's temperature, heat. So you're basically testing how heat sources and how your parts or how your designs respond to heat. Thermal stress is a combination of linear static stress and thermal. So you can put thermal loads on your parts, and you can put static stress loads on your parts at the same time and see how they react and how they hold up. Structural buckling is it's a simulation type specifically designed to simulate buckling. So it's pretty straightforward there. Shape optimization, I'm going to spend a little bit of time on a little later, but basically it is this picture here on the middle right. And what it does is you put in an existing part that you want to analyze, and you put the loads on it, and it'll spit out an optimized version of your part that has less material. It's optimized for mass, and it's removed material in areas where it doesn't need to be. Basically, it's removed materials where it's overbuilt. So pretty cool tool there. And you can kind of see in this photo how there's an outline of the part where it used to be, and then it's like cut away sort of in the middle here. Okay, we talked about nonlinear static stress. Event simulation is simulating loads that are not static. So we talked about how a static stress is like when a load is constant. So you can think of like cars on a bridge as constant, right? There's always sort of the weight on the bridge, or me sitting in the chair as a static stress. A non-static stress would be like if I dropped something, or if I dropped a glass, or if I jumped on a bed, right? Those are not static stresses. Those are you're simulating an event, which is like happening once, and it's higher, usually higher load. You have to factor in acceleration and things like that, some mechanics. So that's what event simulation is used for. And then lastly, electronics cooling. This is probably the one that's like the most different of any of the other types, but it incorporates some convection into it. So it's simulating how electronics can cool, right? So if there's fans, how the fans take away the heat, how the surface area of the parts themselves can dissipate heat, and things like that. So it's related to thermal, but it adds in some convective properties in addition to conduction. So that's a rundown of the simulation types. And I guess the last thing I want to talk about with simulation is just the workflow. So if you're going to go try this in Fusion, all you've got to do is go into the simulation workspace, and then it's going to prompt you to pick a type of study. Then you can, read the descriptions, figure out what type of study that you want. And then like everything else in Fusion, essentially the toolbar will guide you from left to right. So you start by simplifying your model. You add the materials that you want to run it with. Then you add constraints and loads. So this is like the FEA portion, right? You're trying to figure out what forces and torques and temperature gradients and whatever type of study you're doing. You want to figure out what the loads and the constraints are for your part or set of parts that it will see in the real world. So this is kind of the bulk of it. And then contacts, which is only for assemblies, if you're doing a simulation for assemblies. And then finally, you create a mesh of your part or multiple parts, and you're solving, when you solve a simulation study, it's using the mesh to compute the results of that study. So that's why you create a mesh at the end. But that's essentially the workflow. And I can talk through some of this, but the simplified workflow is just to make sure that you're suppressing parts that don't play a significant role in the simulation. So you're only really simulating what you need. You're assigning materials to components. Constraints is constraining the part or multiple parts in its movement, and loads are applying the forces. And then contacts is, like I said, only for multiple components in assembly. But if you have, like, for example, a screw into a plate and you want to simulate both of them for some reason, you need to define how they interact with each other. Are they locked together? Is there a sliding motion? So you have to define that. And then the mesh would just happen automatically when you solved, or you can just preview the mesh and solve it and just create it before you solve. And then once you're ready to solve, you've done all of these steps that you need to do. This checkbox here will have a check next to it. So that is the workflow for FEA. So I'm going to stop there on that topic. Does anyone have any questions about simulation? I'd be surprised if there were really no questions.
Yeah, this reminds me of solid mechanics class. But one thing I wanted to ask is with regards to the different materials that are present. So how vast is the library on Fusion? And can we apply our own, I guess, material properties, or do we have to choose from a list?
Good question. You can create your own materials. Yeah. So the list is pretty vast. Let me pull up Fusion here. Can y'all see Fusion or no? No, right?
No.
Okay, here we go.
Now we can.
Yeah. So here's the material library. So I will expand that. There we go. Okay, so if we look at metal, this is just metal.
Mm-hmm.
That's pretty vast. There's wood, which wood is considered, well, I guess it depends. It's a little more complicated because it's not isotropic. Here's plastic. And of course, I feel like plastic is the case where you'd most likely create your own material.
Yeah. Yep.
So let me show you how to do that. So let me go into the simulation workspace. So it's going to prompt me to choose a type. And actually, look, there's even a 10th type I didn't talk about, which is plastic injection molding. So that's cool. Mm-hmm. So let's, oh, and the other thing I want to show you just while we're here is if I hit help me choose a study type, I can hit a drop down and it'll tell me what each of them do. So this is the new one is see if my part can be properly manufactured using injection molding. That's cool. So I'm just going to pick static stress just for now. And what I want to do is go into the materials, and I'm going to say manage physical materials. And here's my material browser. So this is like a little bit more in depth. So here is the same material library I showed you in the last dialog box. There's like a legacy materials thing. There is, let me try to expand this a little bit. There's an additive material library. There's a nonlinear material library and an appearance library, which is just appearances separate. So if I want to create a new, basically a new library, I could create new library, and then in that new library, I can create a new material.
Mm-hmm.
And I could also, if I want something to, let's say I wanted it to be ABS, or I wanted, let's actually do this. So here's the the material in the document, which is aluminum 6061. And what I can do is I can edit this material. Oh, that dialog box just popped up like somewhere else. There we go. There we go. So this is where I would like see the physical properties of it. And essentially once I assign this aluminum material to my part, I'm essentially making a copy of it. Like I'm having an instance of aluminum in my on my part. So now I can come in and change these properties and show advanced properties as well. So I can kind of make this my own one as well.
So
yeah.
Sorry, so this wouldn't edit the properties in the main library, just in this specific instance?
Right. If you wanted to add a material or change the materials in the main library, you'd have to basically copy whatever you want into your own library.
Mm-hmm.
Because you can't change what's in the Fusion 60 material library. Like that would be a disaster, right? If every user could
true.
basically
Yeah.
edit this master copy. So you'd create your own, you would duplicate the ones you want, create new ones, and then that would be your own library. But you see how all these are locked, right? So that is
Right.
Yeah, that's for a reason. But yeah, totally possible to do that.
Thank you.
Yeah, so here if I'm selecting like acrylic, I should be able to duplicate. I'm not sure why it's giving me a problem right now. Yeah, I should be able to duplicate any of these materials. Carpet, oh, fascinating. Yeah, I'm wondering if, let's go back to the other, this is like the simplified one here. Yeah, so here from this one, I can like duplicate aluminum, edit it, change it to like custom metal, and then, change some parameters or whatever, and then save it. That's another way to do it. Yeah, any other questions? Good question there.
I believe there was a question in the chat.
Oh yeah. To what extent does simulation perform in comparison with other software like multiphysics and ANSYS? What are pros and cons? Good question. So I'm not super familiar with multiphysics, but Fusion simulation is intended to be a tool inside of basically a product development platform like Fusion. It's not meant to be like a standalone high-powered tool. So ANSYS can certainly do do more than Fusion. It's not going to have different results or better results, but it will have more tools to do more with those results. So for example, like when you do a simulation in Fusion, it will give you a lot of analysis tools, right? You can basically have a probe and figure out any point on your part and what the stress is at that point, or what the strain is at that point. It'll give you graphs, you can produce a report. So there's a good number of tools there, but ANSYS has like even more granular analysis. So if you're looking to do like a PhD level thesis around and use simulation for that, I would definitely say like a pure simulation tool like ANSYS or multiphysics is probably where you want to be. But if you're doing like, a simulation as part of a product development process and, Fusion's the types of simulations available and the analysis tools are enough for you, then I think that that's probably easier because it's integrated. But it isn't meant to be, like a standalone simulation tool. Yeah, but like I said, that it's not like your simulation will be will give you different results in ANSYS, but it will probably give you more more granularity on the results. Like you'll get to analyze more tools to analyze your results. And honestly, more types of simulations as well. Like ANSYS does CFD, and Autodesk Fusion 360 does not. But we do have other products like within the Autodesk suite that do CFD. We have a product called Autodesk CFD. It's just not integrated into Fusion yet. And I think the other thing I want to point out about that is that if you go into simulation, you'll notice we actually have an ANSYS button. So we acknowledge that like this, Fusion 360 simulation, while awesome, is not as high powered as ANSYS, and we want to be able to integrate with ANSYS because we know that a lot of our customers use both, use Fusion and do some simulation in Fusion, but then go to ANSYS for more in-depth simulation. So we have basically, we have a partnership with ANSYS, and what that's looking like is we have developers working to bridge the gap. So you can now push your, not just your designs into ANSYS, but you can push your studies into ANSYS. So if you start creating a study in here and then you realize you actually want to move it to ANSYS to do something else, you can just push it to ANSYS, and it'll not only take your model, but it'll take any sort of setup you did. It'll take your materials, it'll take your load cases, it'll take your meshes, it'll take your contacts. So it will take everything you've built in this simulation workspace into ANSYS. And then it goes back too. So if you modify something in there, you can push it back into Fusion. So we're working on developing that partnership more and having even more integration. Yeah. Other questions? Okay, let's talk about generative. Okay, let's start here. So we talked about simulation, and I think the overarching like, I guess, premise of simulation is that you take a part you've already designed and you analyze that part. So, you've already developed concepts, you've maybe workshopped those concepts, you have kind of a working model, and then you want to analyze that working model. And then once you analyze it, you get results, and then you get to decide how you want to change your model based on your results. Maybe it's overbuilt, maybe it's too weak in certain places, but it's very manual, right? You're doing the design, then you're setting up a simulation, and then you have to take those results and then integrate them into the design by changing it however you decide to do that. So that's all well and good and certainly useful. Simulation isn't going anywhere. But generative design, which is what I want to talk about for the second half of today, is a new technology that was really focused on designing for the future of making. So at Autodesk, we talk about this concept of the future of making, which is really what is industry going to look like in 5 or 10 years. We want to make software not just that is useful today, although we certainly want it to be useful today, but really that takes that moves the needle forward and really anticipates where industry is going in 5 to 10 years. And so generative design is a new technology. It's related to simulation, but it's very different. And it's really meant to bridge that gap, to anticipate where industry is going and create tools for that future. So let's talk about what generative design is. So it is a design exploration technology within Fusion 360. And what it does is simultaneously generate multiple CAD-ready solutions based on real-world manufacturing constraints and product performance requirements. So what we're seeing in this image is lots of generative designs. And you're probably noticing like some of them look kind of funky, right? They look kind of organic. They're not typically what we would identify as like mechanical CAD. But there's a reason for that, right? They are generated via an algorithm inside of Fusion 360. So they're computer generated, and they're computer generated based on a set of parameters that you identify. So it kind of mentions that here, right? So this tool will generate multiple solutions based on constraints and requirements that you identify. So you are basically guiding the computer to create optimized geometry for you. So just to contextualize a little bit, right? To rewind, we started with our first CAD tool, our first computer-aided design tool in 1982. That was AutoCAD, and it was 2D. It's on a floppy disk. In the 90s, that's when our 3D CAD came out, right? So 3D CAD is what y'all are learning, right? What I learned, and that's Inventor, SolidWorks, Creo, CATIA, NX. Fusion 360 is a 3D CAD tool, right? And then the next thing is generative design, right? So generative design is more than 3D CAD, because 3D CAD, you're still designing it yourself. Generative design is the next frontier. It's harnessing the power of machine learning and the cloud to aid you in the design. It's what we call proactive design, right? It is driven by a set of parameters, and it requires less work for the user. So it's really delivering on the promise of computer aided design. So we think of this as the new way, right? You as the human plus machine learning algorithms plus computing power, and you get all of these designs. So let's talk a little bit about, actually, I'm going to skip these for time's sake. Talk about the key elements of generative. So like I said, generative is a process by which you are guiding the computer towards optimized designs and delivering a lot of results. And what you're putting in to that algorithm is basically a parameter sheet. You're telling you're telling the software what materials you want the outcomes to be made of, right? So like maybe you want to pick a set of like 5 different materials, and then it'll produce outcomes in all 5 materials. Maybe you want to only do 1 material. Maybe you want to do 10 materials. But you get to identify which materials those are, and it will create outcomes in whichever materials you specify. The other thing you're telling it is manufacturing. You're telling it like basically how do you want it to be manufactured. So if you say when you're setting up the parameter sheet, I only want to create designs that can be 3D printed, then it will only give you designs that can be 3D printed. You could also identify multiple types of manufacturing methods, and then it's going to create outcomes that can be manufactured in different ways. So it'll create outcomes for 3D printing. It'll create outcomes for 2-axis cutting, like water jet cutting or laser cutting, and then maybe it'll create outcomes for 3-axis milling or 5-axis milling if you specify those as well. So for every material and manufacturing method combination, it's going to produce an outcome. So if you have 10 materials and 10 manufacturing methods, it's going to produce 100 outcomes, 1 per pair. So, maybe you'll have an aluminum 3D printing outcome, maybe you'll have an aluminum 2D cutting outcome, but you get to basically take all of these outcomes and then compare them side by side and see what the visual differences are, see what the material property differences are. So instead of, whereas in simulation, right, you're analyzing one part and seeing how it can be changed, with generative design, you're able to create multiple parts simultaneously and then compare them after the fact. And then once you like what you have, or maybe you like a couple designs, then you can export those models and take them back into Fusion and do whatever you like with them. Maybe you want to do more CAD, and edit them further. Maybe you want to run more simulations on them. Maybe you want to go manufacture them. But all of these outcomes that you generate, let's say, let's say in that case, right, you generate 100 outcomes, you could hypothetically export 100 designs and get a fully editable CAD model out of those outcomes. So that, I think I'll stop there. I could talk more, but any questions about generative design? And maybe how it's different from simulation, if that's not clear, or how it's used.
I'm not sure if you would be elaborating a little bit more about like the types of limits or expectations that we set for the software. Like, do we specify what boundary conditions we want it to meet, or the types of stresses it would be exposed to? Like what exactly do we input into the software to allow to design?
Great question. So I did not go into enough detail about that. So we go into the generative design workspace, right? It's right below design, simulations down here. And like in simulation, we go from left to right to create the setup, the parameter sheet, the setup sheet for what it's going to create. So the first thing we would do is edit model. And edit model is basically creating the boundary conditions for our study. So unlike simulation, right? Simulation, we put in an entire finished model and then we analyze that finished model. Like let's say we have a bracket and we want to analyze how much stress that bracket can hold. We're putting into simulation our finished bracket. That is not the case with generative design. Because generative design is a design exploration tool, right? We want Fusion 360 to create the geometry for that bracket. So we cannot put in a finished bracket. If we put in a finished bracket to generative design has nothing to do, right? It's already designed. So like you said, we actually don't want to put in a full model. We want to put in boundary conditions for that model so that generative can actually create the rest of it. And then in letting generative create the rest of it, we're letting generative create the most optimized solution. So, if we're starting with an existing part, we need to basically distill that existing part into only necessary pieces of geometry, which are essentially the boundaries. And if we're starting from scratch, we just need to put in geometry that represents the areas that we need to be preserved. So let me give you an example. Let's say you want to make, actually, you know what? I have an example up on this PowerPoint. So let's go down. So I'm going to give you an example of basically what that geometry input looks like. Okay, so here's y'all can see that, right?
Mm-hmm.
Yep.
So here's a generatively designed part for a motorcycle a motorcycle company in the UK called Lightning Motorcycles. They do electric motorcycles, and they basically want to redesign their swing arm in generative. So this is what it looked like before in CAD. Quite different, right? So when they went to go run this through generative and create this new swing arm, the first thing they had to do was basically set up the geometry for generative design that basically identified two types of areas, I guess. One is called preserves, and that's, I guess, what you're getting at with boundary conditions, right? Preserves represent the areas that you need to preserve as is, that you want them to be in your final generative model, but you want them to be preserved as they are. So in this example, these are the preserves. And if we go back here, we can see those areas, right? It's this box around where the wheel anchors. It's this ring around the motor. And it's these tabs up here that connect to the suspension. And the reason those are preserves is because those are all areas that need to interact with other components, right? Like we can't have generative design create some crazy organic geometry for this bracket because then it wouldn't bolt to the wheel. Same with the suspension, same with the motor. So preserves are basically we want to only put in preserves into our generative design algorithm, because then it allows the algorithm to create everything in between. We're saying, this is what you're starting with. These things need to be preserved as is, but everything else connecting them, you can optimize. And then that's really that's the only necessary piece of geometry that you need to put in. There's a second optional category of geometry you can input, and that's called obstacles. So obstacles are keep out regions, and they basically represent clearances, tool access, any sort of motion state, and assembly features. So all of the light blue here represent obstacles, right? So if we go back to this picture, if we're creating this generatively designed part, we cannot have any material where the wheel's going to go. And not just any material where the wheel's going to go. We can't have any material, maybe an inch out from the wheel, right? Like we want clearance for the wheel because it's moving. So when we're setting up generative, if it's a part like this, we also need to add in geometry that represents where we don't want there to be any generative outcome or any generative geometry, I guess. So we'd model, everything here. We'd model, a block that represents the wheel plus some clearance. We'd model this block to represent tool clearance. We'd model the motor plus some. We'd model the suspension. We'd model this rod that goes through that represents not just the screws, but also like the tool you would need to get into this to fasten the screw. So you're inputting not just the preserves that you want to keep, but also areas that you don't want there to be geometry. So this part's a little bit counterintuitive because typically when you are CADing, you don't CAD the negative space, right? But here we're asking you to CAD the negative space. So going back to Fusion, right? This edit model will, if you already have an existing CAD model, will basically allow you to have a workspace inside of generative design that doesn't propagate to the other parts of Fusion, where you can basically simplify your model so that it is ready for a generative study. Once you do that, you assign preserves and obstacles. Then you do loading conditions. So this part is pretty similar to the simulation space, right? You're setting up how the part's going to be loaded. And then after that, it's manufacturing constraints, like I talked about. How do you want it to be made? Is it with 3D printing? Is it with milling? You put in materials, and for both manufacturing constraints, you can put in multiple. And then the last thing is objectives. An objective is just specifying what the goal is. So for the default would just be minimize mass, but you could also say, my goal is to maximize stiffness. This is my safety factor target or limit. And then you can also put in separate targets or separate limits for modal frequency, displacement, and buckling. And that's basically it. I think, the most complicated part conceptually is probably the preserves and obstacles. The one that might take the most time to do accurately is the structural loads and constraints, which is similar in simulation. And the rest is really just checking boxes, right? Like here's the manufacturing window where you're just checking, which methods you would like, and what orientations in those methods, which correspond to the cube up here. Yeah, let me pull up an example here, but great question. Does that answer your question?
Yes, thank you.
Yeah. Any other questions?
I had one as well.
Yeah.
From after you input all the parameters for it to start doing the generative design, how long does it usually take for it to come up with the actual object or the model? Or does it go through like a certain amount of iterations before it finds that peak model or the optimized model for it?
Yeah, great question. So, depending on so I think I mentioned that the number of outcomes you get is number of materials times the number of manufacturing methods, right?
Hmm. Yeah.
So you could do 1 and 1 and then only get one solution, and that would
Okay.
take maybe 5 minutes.
Okay. Cool.
If you do 10 and 10, it could take 4 hours, 5 hours.
Sure. And I guess does it also depend on like the size or how many parameters or like
Yeah,
fixed objects you have in there as well?
exactly. And
Okay.
how many preserves and obstacles, how many loading
Hmm.
conditions, you can really slow it down. But we do have a solving limit of 24 hours, so after that, it'll fail.
Interesting. Cool.
But it's all done on the cloud. So
That's
it's
nice.
not going to be done locally. Basically, you need an internet connection to send the study to the cloud. And then you can log off, you can shut down your computer, and then, when it's done, it'll be available for you whenever you log on to see them.
Cool. That's great.
So, a lot of people just put the studies in, go to sleep, check tomorrow, or
Perfect.
just put them in the morning, check in the afternoon. But typically, I'm doing a study that's like anywhere from 20 to 50 results,
Okay.
and it takes maybe 2 hours to solve.
Cool.
But yeah, it's not like a simulation where it's instant. It's like generating all this geometry organically, so it does take more time.
Very cool. Thank you.
Yeah, great question. The generated part doesn't possibly seem like very sturdy. Okay, hey, that's an interesting comment. So let me show you a 3-axis milling outcome. So the ones that are really like crazy town, like this one, it's opening, it's taking a little bit, but the ones that are really organic looking, right? That's usually because of the manufacturing constraint that was set. So this one, for instance, right? This would be hard to manufacture for sure. And when I look at what the manufacturing constraints were that created this part, this one particularly was unrestricted. And unrestricted is a manufacturing constraint that says we don't have any manufacturing constraints. So, what you get is going to be highly driven by what manufacturing constraints you set. So this one is unrestricted. This one, however, I'm going to roll back. I did this hole just to show that you can make a hole in it afterward. But this is the result for 3-axis milling. And I don't remember what the I don't remember what the exact parameters were for the study, but I'm guessing this was maybe steel or aluminum, and I'm thinking maybe the load on it was maybe 25 pounds. So this one to me seems pretty plausible. So if you're getting really wonky results that you're like, this isn't sturdy or it's not possible to manufacture, check that it's the right manufacturing constraint that you set. It's not one that you're it's not like you're not, it's not that you set a manufacturing constraint that you don't intend to use. Like, if I look at this and I'm like, oh, I want to mill this, that's not possible because it wasn't a milling outcome. This one's a milling outcome. So this one should be able to be milled. And if it's not sturdy enough, maybe it's true your loads were too low. But in my experience, they do match reality in what I'm seeing. At least, sometimes there are a couple that glitch and then it'll warn you in the kind of results panel, like something went wrong with this one. But typically they are quite realistic, and they do match the manufacturing constraint you set. I think the other thing that I'll add is that what threw me for a loop with generative is that, it's creating all these organic structures, right? And as engineers, we are not taught to think like this, right? We're taught that like mechanical structures are boxy and they look a certain way. And, this is kind of a departure from that reality, right? That we can get really strong mechanical parts that can be manufactured in traditional ways, but they look really organic, they look really skeletal. And the reason that we don't design parts that look like this is because this is pretty hard to CAD. Like the tools we would need to CAD this kind of shape are not typically what we're taught in school. So because we're taught only a certain subset of tools, all of our designs tend to match those tools we have available, right? If our only tool is a hammer, all the problems look like a nail. And that's pretty true with CAD. If the only thing we know is how to make boxes and cylinders, then everything we design is going to be really boxy and cylindrical. So if we had more tools, our designs would look more creative. And I think that generative gives us a chance to really explore having more creative designs. Like maybe I couldn't CAD this on my own, but with generative, I am open to the possibility that maybe this is even stronger than a traditional looking structure. Just because I can't CAD it easily doesn't mean it's not a valid solution. Okay, a couple questions here. Is it easy to adjust a general design, or is it in a phase for suggesting a general structure and make a new model based on the suggestion? So this is a full model. Like this is a solid body. It is pretty easy to adjust it. So this outcome is a T-spline body, right? So these, what we normally create when we create like cylinders and rectangular prisms in CAD, those are called BREPs, boundary representations. And this is a different type of solid called T-splines. So if we, it's this purple button here, it's called form. It's in the form workspace. So if we right click on the timeline and click edit form, it's going to take us to the edit form workspace, and we can, edit these, basically these elements in an organic fashion. So like, let's say I select, oops. I could also just do a drag select, but I'm gonna just show you here. I'm gonna look at it maybe this way. And I'll right click and say edit form. And now I can pull that face out. So this is a type of modeling that industrial designers do all the time, but us in mechanical engineering world don't use this modeling workspace, but it's really crazy. So like, it's like clay in the computer, right? So I can pull it out, and if I hold down an Alt key, I can pull it out and make new faces. Maybe. There we go. Like, let's say I wanted to do that. That's just one thing. Another thing is like, I made this bridge here before. So like, you can do all sorts of things to modify it, fill a hole, crease, uncrease. Like, let's show you that. So like if I double click this edge, let's try that again. It's hard to see here. Okay, so what I did there was just crease an edge. So you can see now it like creased itself, and it's now a hard edge versus a soft edge. So there's all these modified tools that you can do in here. It's not the same as parametric modeling. It's actually non-parametric in the sense that I don't get a timeline out of it, but it's certainly fully editable. Now, this T-spline outcome that you get, this you only get this type of outcome for certain manufacturing methods. So going back to, where did I have that here? So going back to the manufacturing dialog box. So for additive results and for unrestricted results, you get T-spline outcomes. For 2-axis milling, right? So there's 2.5 axis, 5-axis, and 3-axis milling, and then there's also 2-axis cutting. So 2.5 axis milling and 2-axis cutting will give you BREP models. So they'll give you the same type of model that you're used to using in CAD, you know, with sketches and extrudes and things like that. So that's 2.5 axis and 2-axis cutting will give you that type. And then 3-axis and 5-axis will give you, again, the T-spline bodies. And die casting will as well, I believe. So depending on your manufacturing type, it'll give you a different type of outcome. Okay. And then, so he'll ask, do you know what manufacturing process we use for the Lightning motorcycle? I do. That part was done when there was only one type or only 2 types of manufacturing methods. I believe that one was, it was such an early pilot that there only was additive and unrestricted. So I believe that one was done with one of those, and then they altered the design slightly, and then they ended up die casting it. I want to say it was an additive model, but now they would have used the die casting option. Yeah, cool. Other questions? I think I got all of them. Okay, cool. Well, I will end it there then. Thanks, y'all.
Thank you very much, Gabby. That
Yeah.
was very interesting to learn about the simulation and the generative design and the process you have to go through. That's really cool. It's a really neat process.
Yeah, I hope some of y'all end up playing with it and making some cool designs. Feel free to reach out to me.
Awesome. Great. Thank you very much.
Right.
And thank you very much, everyone, for coming today.
Thanks, everyone. Bye.
Bye.